When you build autonomous LLM agents that run for more than a few minutes, you run into a physical constraint. Every tool call, reasoning step, and piece of return data generates an accumulating trail of tokens. Eventually, that data stream hits a hard ceiling. This chart tracks the token accumulation of a standard autonomous session. In 10 turns of back-and-forth execution, an agent can reach 20,000 tokens using the CLAW 100K base tokenizer. That climb breaches standard context window limits, leaving the agent with no room to process its current task. The industry standard approach to this problem is naive sliding window, or first-in, first-out truncation. This method removes the oldest parts of the memory stack to make room for new ones. It deletes history wholesale, often including the foundational decisions and instructions the agent established at the very beginning of the run. Deleting history based purely on time, rather than value, removes the specific context the agent needs to avoid repeating work. Without those early facts, the system often falls into repetitive loops or generates hallucinations to fill the gaps in its instructions. For an agent to run reliably, developers must move away from throwing history away. The goal is a deterministic method to compress memory instead of deleting it. The open-source Agent Memory Compressor library provides a framework to execute this. It addresses the context bottleneck by breaking the problem into 3 modular operations: algorithmic triage, semantic transformation, and automated orchestration. These operations are handled by 3 specific classes: the importance score, the compression engine, and the forgetting curve. Moving away from a strict temporal history to a budget-driven, value-ranked memory store provides a predictable foundation for building agent state over extended runtimes. Before the system can transform any data, it must identify which tokens carry the lowest relative value. That identification is the role of the importance score class. It reads every memory entry in the log and calculates a composite score based on 3 distinct signals. This diagram visualizes the first signal, recency. The system applies an exponential decay curve to the memory stack, ensuring that the newest entries maintain a higher baseline relevant score. The second signal evaluates the specific classification of the data through type weighting. The algorithm explicitly hard-codes system decisions and notes to outrank routine tool outputs. This prevents a verbose API response from overshadowing a crucial one-sentence directive. The final signal is a heuristic keyword boost. Any entry containing predefined, goal-related strings receives an immediate bump in ranking. Combining recency, temp weight, and keyword matches allows the importance score to output a continuously ranked memory store. Because this sorting happens constantly, the least valuable tokens sink to the bottom of the stack. This multi-signal approach ensures that the facts the agent needs to complete its task are mathematically insulated from the automated cleanup. Once the memory store is triaged, the system moves to the semantic transformation phase. The compression engine utilizes 3 distinct LLM-driven pluggable strategies to shrink the lowest scoring entries. The first strategy is summarize. It condenses conversational turns into shorter, fact-dense nodes, stripping filler while preserving core meaning. The second strategy is extract facts. For verbose tool outputs, the engine forces the LLM to distill them into strict bullet points. The third strategy is archive. It replaces the original entry with a minimal reference pointer, sending the raw content to a cold storage database for later auditing. The engine follows a strict hierarchy of destructiveness when selecting these strategies. It is programmed to attempt the least destructive method, summarization, first. It only falls back to archival if the lighter touch fails to recover enough space. To prevent the risk of an LLM summary producing more tokens than the original text, the engine includes a failsafe via tick token verification. Every compression pass is immediately counted. If the resulting text does not genuinely reduce the total token count, the engine rolls back the operation. Semantic transformation provides the necessary scale for memory management, but it requires these strict mathematical checks to ensure the context window never inadvertently inflates. Running this compression pipeline requires orchestration to determine exactly when it is necessary and efficient to fire. The forgetting curve class handles this automation through a dual trigger architecture. This chart tracks both triggers. The first is turn-based. By default, the orchestrator fires once the agent reaches 10 turns since its last memory management pass. The second is token-based. It acts as a ceiling, firing when the total exceeds a 6,000 token threshold. To maintain stability, the Memory Compressor orchestrator incorporates hysteresis. Hysteresis prevents the system from thrashing, repeatedly triggering compression for every new token added. The orchestrator continues to loop until the token count drops significantly below the initial trigger line. During this cycle, the orchestrator addresses the lowest scoring non-protected entries it received from the importance score. It iterates this process entry by entry until the exact predefined token budget is satisfied. This automated, budget-driven loop decouples memory management from time. The system self-regulates based on available space, not the clock. We can now trace how an agent's data flows through the fully assembled pipeline. This diagram shows the complete architecture. The session adapter bridges the stateful agent session manager, projecting volatile session messages into the structured memory store. Once scored and compressed, the context builder takes the compact store and assembles the final prompt. The context builder enforces the absolute token boundary while physically walling off the most recent immediate turns, protecting them to ensure the agent never loses its immediate conversational context. This creates a continuous feedback loop. Data generation leads to a trigger breach, which fires targeted semantic compression, resulting in clean prompt assembly. This final integration step translates unbounded session messages into a mathematically stable data structure, capable of supporting long-duration sessions. In testing, the pipeline compacts a 20,000 token session down to a strict 6,000 token footprint. Alongside this reduction, the critical path decisions and extracted facts survived the compression pass intact. This new architecture represents a fundamental shift away from naive temporal deletion, moving directly toward a deterministic, multi-signal compression model. For developers, this means context limits no longer dictate the lifespan of a session. They can be treated as a managed background process. By managing memory through intelligent, budget-driven compression, we gain the ability to build autonomous, production-ready LLM agents that can operate across extended timelines without failure.